Hey everyone! In this video, we'll touch on chemistry and the built-in chemical data we have that is very easy to access. Specifically, I wanted to visualize periodic trends in the periodic table. Before we hop in, however, let's play a bit with our data to see what we have. In this video, we'll be using chemical data for the entity class elements. Take for example uranium. Outputting the full form of its entity expression shows us that it's a part of the entity class element. As usual, we'll proceed to retrieve uranium's properties. It looks like there's a wide range of properties present. Let's call a few to explore. I was curious, what is uranium's color? Calling the color property gives me that it is silver, which is surprising. I always thought it was greenish. I can get an image of a uranium sample by calling the image property, and I can also call out its crystal structure image. As you can see, we once again have a class of entities, in this case elements, that have properties that are easy to access. With this data, we'll be able to visualize various periodic trends. Here's a general visualization about what we'll be exploring. What we'll be doing is essentially looking at important properties such as ionization energy, atomic radius, etc., and analyzing how they change going across groups and periods. Groups are vertical, while periods are horizontal. Let's start with ionization energy. This is the quantity of energy that a gaseous atom of the element must absorb to discharge an electron. Getting the ionization energy values for all elements, we see the following data. We must note that for elements with atomic numbers larger than 102, this data is missing. We can see that directly by using the cases function applied onto our entity value, calling out the ionization energies. Inside the cases function, the underscore indicates that the first element can be anything, and that we only want lists with an empty second element. We can see that all atomic numbers after 102 have missing ionization energy data. These are our synthetic elements. Now, let's move on to getting the data. Let's interpret this code from the inside out. We'll use the entity value function, and for the entity class element, we'll get a list of atomic number and ionization energies. I will then use the replace all function, indicated by /dot, to replace all empty ionization energy elements with a missing head. This is so that we can plot our data accurately. Then I will apply the map@, function, which will map first onto all the second elements in my data. This is because in importing ionization energies, we get multiple, but we only want to look at the first ionization energy here. The later ionization energies just signify how much energy is taken to get the next electron removed and so on. I can now visualize this data using a list line plot. My most important option here is the grid lines. I will indicate that I want my grid lines to be placed at the atomic number of noble gases. This is to show that these noble gases have the highest ionization energies, which shows they're particularly stable, and also to mark the end of periods. Now we can visualize some trends easily here. As you can see, between any two grid lines that correspond to noble gases, ionization energy increases, which is a trend across a period. For groups, it is not easy to see the trend immediately on this graph, so let's work on a better visualization. Let's make a manipulate to visualize this group trend more clearly. My plan is to set up a slider where I can select groups or periods of elements and highlight their position on the plot. This will allow for an easier way to visualize these trends. The way I'll do that is first begin with a manipulate. After that, I will use a list line plot to plot only the elements in the period or group I selected by using the part function. Then follows a bunch of options, and most importantly, an epilogue with a point at each data point with a low opacity. These will act as my background points. Epilogue is just another option used to add extra graphics to a visualization. Finally, I will denote my keys or options. These will just be the list of all the groups and periods in the periodic table. Evaluating this large expression gives me the following visualization, in which it is easy to visualize the going down groups decreases ionization energy, and going to the right of periods increases it. Now, what about electronegativity? This indicates an element's tendency to attract a shared pair of electrons. Again, some elements are missing here. As we know, noble gases and synthetic elements do not have an electronegativity. I'll start by finding these missing elements by first generating my data and then using the cases function to catch patterns of the form x double underscore, which denotes any sequence of one or more expressions, and a missing head thereafter. And I want the cases function to output only that Wolfram language expression that is before the missing head, which would be the atomic symbol and atomic number. As you can see, we do not have electronegativities for noble gases or synthetic elements. Now let's move on to getting the data. Using entity value, I can set up my data in which the first element is the atomic number and the second number is the electronegativity. Now plotting my data using list line plot, you can see a very similar trend to ionization energy. Between two grid lines that correspond to noble gases, electronegativity increases, which is the trend across a period. Of course, in some periods, we see some erratic behavior. For groups, it is still not easy to see the trend immediately on this graph, so let's work on a better visualization. I can use manipulate to visualize the group trend more clearly. The only different code here is in the epilogue, in which we are deleting cases of missing data in our electronegativity data. As you can see, the trend of electronegativity is decreasing as you go down a group and increasing as you go across a period. Let's move on to atomic radius now. We'll first get the data using entity value to see if anything is missing, and it looks like there are quite a few missing values. However, since they have the missing head, the list line plot will be able to just ignore them. Therefore, I'll just proceed to get the atomic radius data by using the entity value function as usual and visualizing it using a list line plot. This gives us quite a different trend. Between two grid lines that correspond to noble gases, atomic radius actually decreases. This is the trend across a period. Compared to previous trends, we also see the atomic radius is much less erratic. Once again, it is hard to visualize the trend in groups, so let's make a manipulate. We'll use similar code to the last example, but different labeling. Last but not least, we'll look at electron affinity by first getting the data using entity value. Electron affinity is a measure of the likelihood of a neutral atom gaining an electron. Since the missing data here also has the missing head, we can proceed to plot it using list line plot. We can see a rough trend here, but it seems more erratic than the other trends. To get a better look, let's visualize these trends using a manipulate. It looks like as you go down a group, electron affinity decreases, and as you go across a period, it generally increases. I encourage you to explore even more periodic trends on your own now.